We're surrounded by these invisible forces, right? Silent engines humming away in our kitchens, our offices, our factories, literally turning our world. But what is this hidden power? What's the secret behind all that spin? I mean, really, what is it that literally spins the fan above your head, blends your morning smoothie, or powers the massive conveyor belts that build pretty much everything we use?
Well, the answer, more often than not, is the good old AC motor. And its operation is all based on this fascinating, invisible chase, an electromagnetic game of tag that we're about to break down.
Okay, so to really understand the motor, we have to start with the fundamental bit of magic behind it all, and that is the principle of induction. Check this out. This is a classic physics demo called Arago's disk. It looks super simple, but what it shows us is mind-blowing. A spinning magnet can make a metal disk spin without ever touching it. It honestly looks like magic, but it's a deep, fundamental principle of physics. So how in the world does this work? Well, it's this beautiful three-step dance. First, as the magnet moves, it creates a changing magnetic field. Simple enough. Second, that changing field induces an electric current in the metal disk. And third, this is the kicker, this brand new current creates its own magnetic field, which then interacts with the first one, generating a force that literally drags the disk along for the ride. And that right there, that's the whole secret sauce. Electromagnetic induction, creating a force without any direct contact. Just burn this idea into your brain because it is the absolute key to everything we're about to talk about. So how does an actual machine use this principle? To figure that out, we need to meet the two main components, the two main players in this story, the stator and the rotor. So every motor has these two essential partners. First up, you've got the stator. It's the stationary part, the housing, and its whole job is to take electricity and create a magnetic field. Then there's the rotor. As the name suggests, this is the part that actually rotates. It's the spinning shaft that's built to react to the stator's field, giving us the useful motion we're after. Okay, so we have a stationary part and a rotating part. But how does the part that stays still make the other part spin? Well, the secret is in creating a spinning magnet, but out of pure electricity. And this is where it gets really, really clever. Most of the bigger AC motors run on what's called three-phase power. So instead of just one single alternating current, you get three separate currents, all perfectly overlapping but staggered 120 degrees apart from each other. And when you feed these currents into the stator's coils, they team up to create something incredible, a smoothly, continuously rotating magnetic field. The electricity itself creates the spin. Yeah, three-phase power is just elegant. It naturally creates this perfect rotating field. But what about the single-phase power that we all have in our homes? Well, it can't pull off that trick on its own. It needs a little help. So, single-phase motors have to use an extra component, usually a capacitor, to kind of fake a second out-of-sync current just to get the rotation started. Okay, we've got induction, we've met the stator and rotor, and we know how to create a spinning magnetic field with electricity. So now, let's put it all together in what I like to call the Great Chase. And here is where it all just clicks into place. Remember Arago's disk from the beginning? Well, the stator's rotating magnetic field is our spinning magnet. And the rotor? The rotor is our metal disk. It's the exact same principle of induction, just brilliantly engineered into a powerful, practical machine. Here's another really powerful way to picture it. Think of the motor as a transformer. The things that change voltage. But it's a transformer where the two halves are separated by an air gap. The stator induces a current in the rotor right across that empty space, transferring energy without any physical connection whatsoever. But for this induction to work, there is one critical, non-negotiable rule. The rotor can never spin at the exact same speed as the stator's magnetic field. There has to be a small difference, a little bit of lag, and that difference is called slip. Think about it. If the rotor ever caught up completely, the magnetic field wouldn't be changing relative to it anymore, and the induction and the torque would just vanish. So that slip is absolutely essential. And this is precisely why these motors have another name, asynchronous motors. Asynchronous just means not in sync. The rotor is forever chasing that magnetic field, always a little behind, never quite catching up. It's that constant out-of-sync chase that creates the torque that powers our modern world. Okay, so we know how to make it spin. That's awesome. But what if we need it to go faster or slower? How do we actually control it? Well, a few things determine a motor's speed. First is the number of magnetic poles that are physically built into its design. That's pretty much fixed. Second is the load on it. A heavier load will cause more slip and slow it down a bit. But the real key, the variable we can actively control, is the frequency of the AC power supply. If you can change the frequency, you can change the speed of that rotating magnetic field. And we change that frequency with this device, the Variable Frequency Drive, or VFD. This thing is basically the motor's brain. It takes the standard power from the wall and precisely tweaks the frequency it sends out, which gives us incredible control, from a slow, gentle crawl to full blast, all while being super efficient. So the big secret isn't magic, after all. It's just an invisible chase governed by the laws of induction and slip, and all of it precisely controlled by frequency. Now that you know how it works, think about your day. How many of these tireless spinning motors can you spot, hiding in plain sight, just quietly powering the world all around you?